Hello everyone and welcome back. In this video, we'll be discussing the torsional pendulum and looking at a few sample problems. A torsional pendulum consists of a rigid body, meaning something that has mass, that is suspended horizontally by a string or thin wire. When the pendulum is rotated some angle theta in radians, it'll twist back and forth about its equilibrium position. The period of the torsional pendulum can be calculated with the equation T equals 2 pi square root of I over kappa, where I is the rotational inertia of the object and kappa, which is the Greek letter K, is the torsional constant of the string or wire. The torsional constant kappa is very similar to the spring constant K. A large kappa value means the string or wire is stiff and does not easily twist, while a small kappa value means the string or wire is easier to twist. And as expected, the torsional pendulum oscillates in simple harmonic motion as the restoring torque, which is equal to negative kappa theta, is proportional to the angular displacement from equilibrium. Let's look at an example problem. A torsional pendulum consists of a 2-kilogram disc with a radius of 40 centimeters hanging from a thin wire passing through its center of mass as shown. The torsional constant of the wire is 25 Newton meters. The pendulum is set into oscillation by twisting the disc 1.5 radians. Letter A, calculate the period of oscillation. So we can find the period by using the equation T equals 2 pi square root of I over kappa, where I is the rotational inertia of the object, which in our case is a disk. So that's going to be a 1/2 mr squared. So plugging in my numbers, I have 1/2 the mass of 2 and a radius of 0.4 meters over torsional constant of 25, and I get a period of 0.5 seconds. So that means that when the disk is hanging from the wire in equilibrium, the wire is not twisted at all. But then I take the disc and I twist it. I move it 1.5 radians, and that twists the wire. And then when I let go, it's going to spin back or twist back and come back, and that's going to take 0.5 seconds. Letter B says, calculate the restoring torque at maximum displacement. So just a reminder that when you're at equilibrium and you twist it just a little bit, your restoring torque is just a little bit. But when I twist it even more, the restoring torque continues to grow. It's not a constant relationship, it's a linear relationship. And so I can use the equation tau equals negative kappa theta. But I want you to see that this restoring torque equation is kind of analogous to Hooke's law, which was F equals negative kx. So instead of displacement x, we're going to have an angular displacement theta. And the negative sign just tells me that the restoring torque is acting in the opposite direction. So I'm not going to need that negative sign in my calculation for letter B. So the restoring torque is equal to the torsional constant, 25, how twisty the wire is, and the at maximum displacement, which is 1.5 radians, I get a maximum restoring torque of 37.5 Newton meters. All right, letter C says, write an equation for the position of the disk with respect to time. So we did this before where we wrote a position function, x equals a, and then it was sine or cosine of omega t. So we're going to do the same thing, but this time with rotational displacement. So I have theta equals, we don't really have a variable for maximum amplitude, so I just wrote theta max. And I have to pick between sine and cosine. And I picked cosine because I set this into oscillation by twisting it off to the side, so I was at a maximum amplitude there. And then I took my omega and I broke it down into 2 pi f. So now when I plug in my values, my maximum displacement is 1.5 radians, 2 pi, and frequency is 1 over period. So that's where I got this from, 1 over 0.5. So then I just simplified this, and that turned out to be 4 pi t. So theta equals 1.5. Cosine of the quantity 4 pi t would be the equation for the position of the disk with respect to time. So that would tell me at any time during this motion, I could calculate exactly where the disk would be. And one more quick example. A 3-kilogram rod that is 0.4 meters long is hung from the ceiling by a wire that passes through its center of mass as shown. The rod is displaced 10 degrees from equilibrium and released. If the rod oscillates with a period of 0.75 seconds, calculate the torsional constant of the wire. So we can find kappa using the period equation, T equals 2 pi squared of I over kappa, where I is the rotational inertia of the rod. And since the wire is passing through its center, the rotational inertia is 1/12 ml squared. So plugging in my numbers, a mass of 3 and a length of 0.4 squared, I can complete that. And since I'm solving for kappa, which is in the denominator under the square root sign, I chose to square everything just to make my algebra a little bit easier and got a torsional constant of 2.81 Newton meters.